So we'll start off with list ADT. So what is a list? A list is just an ordered sequence of some elements. And in a list, you can you can only do the basic operations we covered: insertion, deletion, searching, and traversal slash indexing. So for insertion, let's see. We have we can insert at any position. I'll just write it. So we can insert an order. Fine. Now you can also insert at any position. So in we are going to be using zero indexing. So 0, 1, 2, 3, 4. Let's say I want to insert 6 at position 4. What happens then is you get 6 here and the positions shift. You can also perform deletion from the middle. Let's say we delete 3. Positions shift again. And you can perform search. Let's say we want to search for 4. You can do linear search. You can't do binary search here because this is just not sorted. You would just start at 1, 2, 6, 4, and you get 3. And you can do access by indexing, and which then you can use indexing for traversal. So that's all there is to LSTDT. You can insert, search, delete, and index. Now we have multiple ways to implement this ADT as a data structure. The first one is based on an array. For that, we will set a attribute, and we have insertion, deletion, search, traverse, and indexing operations. And for the array-based implementation, we will have a maximum length because our array is static. It has a constant maximum length it can allow. For insertion on an array-based list, and complexity is often absolute space complexity is often appending, and appending would give you the best case. So adding on to the list is constant. Appending and on the beginning of will give you the worst case, which is open. So okay, let's look at the list as full function. This full you just check list length maximum, and this empty is just list length is 0. Now If it's full, we return -1 to indicate failure. We cannot insert any more elements. If the position is not a valid index, we cannot uh, insert it. Otherwise, we take I to be the length of the list and then iterate down from I till position and shift items to the right. So let's say we have a list. Let's say we have 1, 2, 3, and we want to insert 4 at index 1. So what would happen is 3 would go here, 2 would go here, and we can now insert 4 here. So that this is while it was going. It's just shifting items to the right. And then you're just inserting 4. And then you're increasing the length of the list by 1, and then you're returning 0. Now the step count for this is 1, 2, uh, uh, 3. You have two comparisons and an OR. So 1 again. This is 1 times. S- let's assume the worst case, it has to insert at the beginning. So it will be n and then 1 false check. So it's going to be n plus 1. So this costs 2 addition n assignment. Another 2. 1, 2. Now sum it up, you get 3, 6, 8. 8 plus 5n plus 1. And space complexity, you get, uh, let's see, this gives you n. These two give you 1 each. This gives you 1. And that's it. So you have fixed place complexity of n plus 3 and no auxiliary space complexity. Deletion, similar idea. If the list is empty, we can't delete from it, we return. And valid, we have a valid index check. And we store the element to return at the end. Then we do the opposite. From I, which is position, from which the element is to be deleted, till the end of the list, you keep shifting elements to the left. So the opposite of what you did here. We shifted elements to the right here from index plus 1 to index. We do the opposite. We say the index is index plus 1. So you're just continually shifting elements to the left after which essentially deletes the element. So the step count is going to be almost exactly the same. And the space count is also going to be the exact same. You have n from here, 1 from here, 1 from here, 1 from here. And yeah, that's it. So n plus 3 again. So the step count is going to be the exact same here too. And then searching, you just do linear search. You already know the complexity for this. And these are supposed to be unseparate lines. So space complexity is also getting the element is just a shim for the index function. Yeah, sorry, not index function, indexing. So we just do an index check and then return it. Uh, you can do the cost for this. It's just 3 and 1, 4. SMT is full. We already saw it's just a single check. And that's the array-based implementation. For a single linked list, we have the extra assumption that we have a node for each element with data and next pointers. And the list object additionally contains head and tail and then len, obviously. So insertion, we do the normal index check. We create the new node. And if we are inserting at the head, that is if position is 0. So this is intended wrong. No, anyways, this is supposed to be lining up here. Uh, yeah. Yeah. We create a new node, and if we are inserting at the head, we set the new nodes next to be the head of the list. And then we set the head to be the new node. So we have inserted it. And if the tail pointer is none, we just set the tail to be head if we're inserting into an empty list, that is. If we are if the position is the length of the list, that is we're appending, we just set list tails next is the new node, and then the tail is the new node. And this else is supposed to be here. And this else is the case where uh, we are not inserting at the beginning or the end. We are inserting in the middle. If you're inserting in the middle, you just start from the head and iterate up until the previous node of the insertion. You just do current equals current dot next continuously, and then increment I to keep track of which node you're at. And then you set the new nodes next to be the current nodes next, and then the current nodes next to be the new nodes next. So we have some amount of elements. You have the current point to by current dot next. Now we have a new node. So we are just removing this and make this to perform the insert. And then you just increment the list's length and return. Deletion. You do an underflow check with SLT, and you check the indexes within the allowed range. If we are deleting from the beginning, we just store the value stored in the beginning and set the head pointer to be the next element. If you're not deleting from the beginning, we just start from the head, same deal as before, iterate up. Now what you do is, you have a bunch of elements. You have C dot n, another element, C dot n dot n. You're removing this, creating this. So this middle element is deleted. And if you or deleting the last element, you just update the tail pointer to be the previous element. And then you reduce the length of the list by none. And then you check if the length of the list is 0, then you set the tail pointer to null as well. You don't say, need to set the head pointer to null because that's taken care of here. This next will be null if there is no. Searching, same as linear search again, except instead of indexing, you just do current equal to current.next. Best case and worst case are same, starting and not found. Indexing, you have to iterate. Unlike in an array, you don't have constant time indexing in a linked list. You do an index check and then iterate up to the index and then just return it. If empty check, you have this dot head equals null. You don't have a useful check because um, linked lists are unbound, have unbounded growth. Next, W linked lists. Yeah, W linked list. The extra assumptions are we have a previous pointer now on top of the other assumptions. For insertion, pretty much the same as the single linked list one, except you're setting the previous pointers for the nodes. Everything else is the exact same. Insertion at the beginning is special cased, insertion in the end is special cased, and insertion in the middle is the same. Deletion, uh, almost the same as in a single linked list, except for deletion at the end also, you can also do it directly, hence the best cases, both head and tail as opposed to just the beginning. Uh, you do the empty index check and then just iterate up to the index, and then either special case list length. If the position is 0, you just set this, and if the position is the last index, you just set tail to be the previous thing, and list dot tail dot next is null, and then you just return the element. Search is also the same as an linked list. Getting is different because you can choose to start from the beginning or the end in a doubly linked list. So based on the index, wherever is closer, we start from there and iterate upwards or downwards, depending on which is closer. This empty is also the same as a single linked list. In a circular linked list, it's almost the same algorithm wise, but if you're inserting at the head, you don't get to just insert at the head and forget about it. You have to go through the entire list and then set the tails next to the new head. Otherwise, it's pretty much the same as a normal insertion in a linked list. You cannot special case the last index insertion here. Deletion. Deletion is also mostly similar. Uh, Normal checks. If the length is 1, you just delete it and set it to null. If the position is 0, you're inserting at the head or deleting from the head. You just set the tail, you just find the tail and set the tails next to be set the head to be the next value and then set the tails next to be the new head. Otherwise, normal deletion. Searching, uh, you have to keep I track of I and search through the list and terminate. Otherwise, you'll end up in an infinite loop. Otherwise, it's pretty much the same. SMT is also the same. All right. For stacks and queues, I give it back to AJ.
All right. Okay. So let's see. Stacks and queues. These are efficient for operations that are happening at end ends of the data structure, right? That is beginning and end. Uh, so if this is your structure, these will make it efficient for these two parts. It does not care about the middle at all. So in case you need to work with something that mostly deals with like the last value or the first value all the time, would you'd go for this. Let's start with stack ATT. So this follows last in first out principle. That is, just like a box you uh, put in your first book, second book, third book. You have to take it out in the opposite order for you to access the beginning again. That is the main principle of it. Um, so what you do here is what you need to store and what are the operations. You need to keep track of what is at the top of stack, right? That is one thing you need to do. So if the stack has A, B, C, what you will know is this is the top. You will not know anything beyond that. You will know this is top and that only. What operations you can perform on this is push, that is your adding element to top. Pop, that is you are removing element from the top. And then there is peak. Peak is just view element from the top without disturbing it. So when we talk about stacks, right, there are two concepts here. Um, so not just for stacks, but still, there is something called. Let me let me go here itself. Uh, Underflow and overflow. You must have heard these terms from popular websites at least. So, when a stack exists like this, but there is no elements left, and you try to pop again, what's gonna happen? Like, there is no elements left. So, this is the case for underflow. Overflow happens when there is a limit on the size of the stack, and only then that will happen. So, there must be limiting maximum size of stack. So you can visualize this by imagining you have a box, you can only store 5 elements in it. So in case you have already stored 1, 2, 3, 4, 5 in here, um, and you want to push one more time, you cannot do it. Further push is not possible because it's already full. Okay, so that is two concepts. Let's go for array implementation of stack. So, first thing about array implementation is that you need to know what is the st size of stack you're gonna take, right? So, max size n. You need to decide this n before you even start populating the stack. That is there. Since this exists, overflow might happen also. Uh, that is, stack can become full, and you may not be able to push further. Um, so, and the top element uh, is added from back of array, right? Let's visualize this. So this is your normally how you would think of an array. Let's do this. Take the same thing. Let's rotate it. Let's make this a little bigger also. Uh, and same indexing only. Let's just write it as 0, 1, 2, 3, 4, 5. Right. Here, array of size 6. So, elements will go in like this and they will come out like this. So, here, this top right, you can keep track of it using index. Top index you will keep track. So, initially, uh, top is equal to -1 when there is no element in the stack, right? And then as soon as one element is added, let's say you push A, then A will come like this, occupy 0th index. That I'm just saying for visualization. In actuality, it will just be directly assigned uh, whatever is current top plus 1. So now uh, this will be top 0. Right, I'll write it that side, top. Now, if you push B, again, B will come, it will be assigned this plus 1. B will be here, this will be your new top. Like this, it will go on. One thing you need to keep in mind when you're pushing is you need to see if maximum size of stack is already reached or not, right? So that is the one thing you need to keep track of, right? Uh, so that is push. When you pop now, um, the element of the top will be deleted and top index will decrease by 1. This is the only major concept, nothing more than that. So okay, let's just look at the algorithms. Uh, okay, first is push. Here we can see first for push you have to check the full condition. If it is full, you cannot add it, so you just return. Otherwise, you increase the value of top like we did and insert there, right? So let's do step count. Uh, is full operation is just O of 1. You just have to check if top equals n or not. That's all this full condition is. Um, these two operations, this is 1. So step count will give you 3 over here. And we can see that this is in constant time only. Here, space also. Space also nothing more is used. So no extra space, right? Let's see push. Um, Push also you have to check for underflow here. That is also you just have to check if top double equals minus one. That is your empty check, right? Let me just top equals minus one when empty. Top equals n minus one when full, right? Um, so this will give you one. This will give you one. This will give you two. So yeah, here time also is constant here also. 4 it'll be there. And then space, this is the only extra and it is fixed. Um, so auxiliary space is nothing is has to do with n. So that's taken as constant auxiliary space. Um, let's take peak. Here is empty check, uh, or we'll take one count, and that's it. So time is still constant count, and yeah, that's it for peak. Is empty is full. This is what I already explained. These are the two conditions you need to check for push and pop or peak, respectively. So that covers array implementation. I think from this you should be able to write the algorithms by yourself because it's not that complicated since everything is just like 2 or 3 lines. Let's see link. It's not okay. It's okay. Singly linked list implementation. Um. Uh. So here there is you can have how many other elements you want. There is no limit because dynamic memory. Um, so here also you need to keep track of top of stack. This is the same as your head pointer, right? So initially uh, top will be null when empty, and there is no full conditional. So this is what it is. Um, Visually, uh, first it is like this. Top points to null. Uh, you push A. Now it will be you'll have node A that will point to null, and top will now point to A. Push B. Now what will happen is um, you will create a node B. Um, you will let B point to A, and this top you'll make it point to B. So push happens so. Uh, Pop, you just have to just map this to, I'll just duplicate that real quick. You just have to uh, point top to A, that is uh, top of next, and then just delete this, right? Um, Peak is just uh, top dot data. That will give you the first element if it exists. Otherwise, it will set fault on you. So first we have push. You create a node. You make the uh, um no, node point to the next of the current top, and then you reroute the top to point to the node. Node, okay, first top points to uh, some node. Node now points to this. You make top point to this new node. This is the logic. This also we can see one constant time only. So time is of one. Extra space is required, fixed. So there is no auxiliary space. Um, Here, pop, right? Yeah, pop and peak, you need to still perform this check because underflow is still possible. So this check will take one. Um, you take the data, put it in a variable. This is one, and then you make the top point to the next node, right? This is one. Still, time is still constant, and auxiliary space is also nothing is based on n, so it's fine. Then we have peak. Same check. You just don't do the updation for the top. There's not much difference. Same thing as this. And is empty check is just null check. Nothing more than that. Constant only here also. So that covers linked list. Um, so now we have applications. Common applications are infix to postfix expression conversion, right? This we have. We will be covering this tomorrow only, okay? Then we have function call stacks uh, used in memory. And then you have syntax validation questions like given a sequence of brackets, check if they are valid. For this, you will use stack only. You will push, and whenever there's a close bracket, according to mapping, you will pop it if it matches. If it doesn't, you'll just return false, something like that, right? Then you have undo redo kind of systems where you use two stacks. One stack for undo, one stack for redo. You just put this there, put this here, according to whichever is doing push and pull, push and pop. Sorry. So yeah, uh, final conclusion is here. Uh, all stack operations take O of one time and O of one auxiliary space, right? So let's move on to Q. Um this is first in first out principle. It's a just a queue of people. You line up in front of the door. You go one by one according to who came first. And that's the principle. So what you need to have is the front of the queue and the rear of the queue, right? So you need to know this and you need to know this. Uh, and then operations, you have NQ, DQ, and front or peak, whatever you call it. NQ, you will uh, insert at rear. Will this be rear? This will be front. DQ, you will remove element at front. Peak or front, you will just view. the element in the front. Those are the main operations. Let's look at array implementation, right? Okay. So again, just like stack, uh, max size and you need to know this before. Therefore, like here also, there will be there might be overflow here also, right? So you need to check that. Uh, so front and rear, you get to know this with the indices to keep track of front and rear. Initially, front is equal to rear is equal to -1. Let's visualize this. So you have an array. It's a little too big. Let's just have 1, 2, 3, 4, 5. So initially, front equal to -1, rear is equal to -1. Uh, so now when you NQ one element, right? So A goes here. Now 1, 2, 3, 4. Front will be 0, rear will also be 0. When you NQ one more element, front will remain the same, rear only will change, right? Like this on, imagine I added till here, right? Rear is that till here. And then I am dequeuing. I am dequeuing 2 times, right? First time I dequeue, I will remove this. I will move front here. Second time, I will remove this. I will move front here. Now, um, okay, imagine there is one more element here itself and the rear is here right now. What happens when you NQ one more element? Um, since there is two spaces here, it doesn't make sense to stop it right here. So what happens is, this will now wrap around. So the flow goes like this. This is the actual how Q is going. So F is at the back, C is at the front. Right. And then goes like that. And then if you add one more element, now rear is here, front is here, Q is full. Full Q check is Q is full now. Rear plus 1 mod n. This is because we are wrapping it around is equal to front. Right. Empty check is just this -1. Right. Let's look at brightness. Okay. Algorithms. NQ. Always at NQ, you will do one full check, and then you will update the rear, add the element in the new rear, right? That is fine. Step count, this will contribute 1. This is 1, 2, 3. This is 1. Here also it's a constant time and auxiliary space only. Let's take DQ. Um, Again, DQ you have to take, you have to check if it is empty already. That will just be 1. This will take 1. 1, 2, 3 operations, 3. Here also it's of 1 only. Peak. Similar to DQ, except you don't take the element off, right? this is just is empty, and empty is just front is equal to rear is equal to minus one. Right. So this will take one. That's it. So time here also is O of one, no auxiliary space here either. Uh, Full empty conditions we've already covered. So this is array implementation. Uh, Single linked list implementation. Here again, no memory constraints. Any number of elements. Um, Here, front and rear are pointers, right? So front will be the head of the linked list, and rear will be the tail. Sorry, I think I got that. Mhm. You NQ from okay, you NQ from here. So um yeah. Uh okay, okay. Rear tracks the last node, NQ, DQ from the front. Okay, DQ from the front. Okay, I was right. This will be head, this will be tail. So um first, front and rear both are null, right? One element comes in, A. Um, Front points to this, rear also points to this, this points to null. NQ one more element. Um, so front will point to B, this will point to A, this will point to null. Mm, Sorry, this is here, this is here, and yeah, this is rear. You NQ once more. It will only consider this since you already have the rear pointer here. It will just be like this. B will point to one more thing, C, and then it will point to null. This remains untouched. Right. When you want to DQ, um, similar thing as stack. Front will point to this. This will just simply be taken away like that. Okay. So that is NQ DQ. Front is just you take front dot data. That will give you the element. Again, you have to do empty check for this, and you have to do. You don't have to do full check because there is no condition for full. So empty now. Um, uh, F will be. This is all you need to check for that. Let's take this. You create a node. Uh, if if the queue is empty, um, you will assign front to this. Or if it is not, you will just take the current rear, make that point to this node, make this point to null, right? And then you will update rear to make this, right? When you see complexity, step count will take. Here also, this is one, 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 everything is one. This is also one. Okay, DQ already demonstrated. You check empty condition, uh, take the front element, reassign front, and then update rear if necessary and it becomes empty. Step count here also, it will give you O1 only. For time, auxiliary space, nothing is used, so that still remains O1. Peak or front, you just have to do uh, empty check, and then you just return this as it is, O1 again. And empty check is just this one condition. That's all it is. So that we've covered that. Application of queues include scheduling algorithms like anything that needs to go in like first come first serve basis, right? And then it is also used in breadth first search. This will see in trees and grass, traversals, and search, right? So here also we have seen that queue operations also everything has O of 1, uh, time, and auxiliary space. So let's look at this table here. So here we can clearly see that all operations here are O of 1. Isful is only there when there is an array implementation due to um, size limit, right? Otherwise, linked list and all, it's not used. So comparison, array is contiguous memory, linked list is dynamic. Due to that, we can see the differences here. Yeah, overflow you need to check due to it being fixed, right? Then underflow you need to check for both. Extra space, since array allocated all at once, for each node you don't need to add anything to memory. Here only whatever you need is taken. So every time you add an element, you will take one more space. So that's what it is. Here we have optimized O of 1 only at ends, right? Middle still remains to be O of n, as you've seen from this. Can we do this better? We're gonna see that using trees. So I'm gonna just hand it over to Narendra.